I'm going to talk a little bit about Rn. So Mn over Bd squared. Uh, think of this like this. Remember that stress equals My over I. And if you take y as the distance to the top or bottom, we call that C. And if you took steel design, I over C is called S, section modulus. Okay, so so M over S is a stress. Section modulus is I over C. This is like in inches. This is like in inches to the fourth. This has units of inches cubed. Okay, so the moment divided by something in inches cubed will equal to stress. Well, look at this. Mn over Bd squared. That's very much like a section modulus. In fact, let me add a page here, continue this discussion. Okay, okay. So let's just talk about this Mn over Bd squared. Let's take a rectangle, okay? Let's call it B times D. I is 1/12 B D cubed. C, the distance to the top, is D over 2. So S, which is I over C, is 1/6 BD squared. And so M over S for this rectangle is M over 1/6 BD squared. So you see this thing here? That's that. Okay, so Rn is like the moment divided by a section modulus. And the units of that are stress. Okay, okay, so the units of Rn are stress. And so let's see if that's true. Let me copy this equation. Bring it down here. Oh, didn't work. Okay, let's see, I'm gonna just have to write it. Rn equals Fy rho 1 minus Fy rho over 1.7 F prime C. Yep. Okay. This has no units. The Fy and F prime C units cancel out. That has units of stress. And rho has no units. So that has units of stress. There you go. So that's an interpretation of Rn. It's like the moment divided by a section modulus. Okay, let's continue. There's two forms of this, okay? A convenient thing is this. This is called mechanical reinforcement ratio, omega. And to help you understand that, let's expand rho. So it's Fy F prime C. Remember rho was AS over BD. So it's kind of like steel stress times steel area divided by concrete stress and concrete area. That's what this is. Or you have M, okay? M is just the ratio of steel stress to concrete stress. Okay, so you can make this substitution and then you get this. So this is a handy equation. Or you can make that substitution and get this. So the three options are the original equation, Rn equals Fy rho 1 minus Fy rho over 1.7 F prime C. That's option 1. Option 2 is using this omega, mechanical reinforcement ratio, or option 3 is using M, which is just the ratio of steel stress to concrete stress. What's really important is the inverse. Okay. This is actually a quadratic in omega. And this is a quadratic in rho. Okay. And so if you take the quadratic formula, x equals negative b plus or minus square root b squared minus 4ac. I don't remember it. But if you do the quadratic formula and solve for omega or solve for rho, you get this. This is extremely handy to have, okay? So lastly, we're gonna do some approximate expressions. Z, d minus a over 2 typically comes out to 0.85 to 0.9 d. And if you start with this, and I'll give you some kind of bonus extra credit if you can derive this, and you start with the MN equation and solve for AS. And this is often what we have to do. We have the moment, we know the size of the beam, we want to know how much steel to put in it. And if you take your MU in foot kips divided by 4D in inches, that will come out to the required amount of steel in inches squared. This is a pretty handy thing to know. Do not do your calculations solely based on this. Do the calculations I'm about to teach you for design, but I would do this on a piece of paper on the side before I do anything. And this will tell you if the answer you got in the end is correct, in the right ballpark. Okay, so there we go. To summarize, you should have these three forms, one of these three forms of Rn. I would put them in a calculator. I personally have this one. So this one is on my calculator. And what's handy, I have a calculator that I can put the variables in, and I can solve for any variable in there. If I put all the other variables, I just have this solve thing on my calculator. If you have a calculator like that, I highly recommend you I would put this equation in. I've thought about all three of those, and this equation for me has been the most convenient. Okay, so that's it for now. When we do some design examples, the utility of this equation will become more apparent. So until we start doing design of beams, you don't really need to know this. When I actually calculate MN, I just do T equals C, solve for A, Z is D minus A over 2, and MN is T times Z. But when I design the beam, I do use this equation that we just derived. Okay, so that's coming up shortly.